All right, crew, here's a challenging one. It's from the advanced book. And so in our book, it's chapter 9. It's on torques and equilibrium, which is the chapter 12 at the university physics book. And it's number 78. And it's talking about this here. It says that weight are gradually added to this pan until the wheel of mass capital M and radius capital R is pulled over an obstacle. So here's kind of like a little curb or some kind of obstacle of height D is shown. What is the minimum mass in this weight pan plus the pan needed to accomplish this? All right, well, the easiest part of this is to really say that if we're just going to barely make it and kind of twist over this curb right here, then the tension here is the weight in this pan. Because over here, if we did a free body diagram, the tension up would have to equal the weight. So that's probably the easiest part of this problem, is just to recognize that the force we're getting from this cable or rope here, which is tied to the center of the wheel trying to get over the obstacle, is equal to the weight of that. So I'll just call it tension, and we'll solve for tension. Now if we do a free body diagram, we'll have something that looks like this. We'll have a tension here pulling to the right. We'll have gravity, capital MG, pulling down. There's a contact here, so you might say there's a normal force. And maybe I better call that normal force number 1, because there's also a contact here, and maybe I'll point it in this direction. Not real sure, since it's not a flat surface, and that's going to be something to think about. Let me call it normal number 2. All right, so let's just talk about our free body diagram. It should be gravity, good, and everything touching it. So touch, 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 and that's it. Okay, so I got the free body diagram. There's 4 forces here, and luckily, if I read into this, it's saying just enough to lift it over. So not really make it accelerate as it pivots over here, but just enough to maybe overcome the contact here. So what I think I can conclude here, and this will be a major step, is that contact point has a force of 0. It's just, you might say just enough, and it might take an infinite amount of time for it to roll over. But the point is, it's not contacting here anymore, so you can't have a force. Now, there is a contact here, so you do have a normal one there. But that's good too, because remember that nice little trick we learned about torques. That if there's a force that you don't want to solve for, and you don't know much about it, calculate the torque around that point, because torque is calculated, and we have these 2 formulas, R, F, sine theta, or R perpendicular F. But either way, if you pick, say, this point right here to be the pivot calculation, which really is the pivot point too, so it's kind of a no-brainer to pick that one. Here, whichever formula you want to use, you would call R equals to 0, and the torque would get 0 here. And so that would not come into play. And so with the first normal force being 0 and this one not coming into play in our equation, we actually then have something a little easier to work with here. And I say not known. The truth is, all of these, nothing is known, because they gave it all in symbols. But the general rule is to try to, get your answer in the symbols they've given us. And so these other 2 forces, the tension, which is the weight they're looking for, and the weight, mg, is given in terms of our parameters here. All right, so I like what I have here. In fact, maybe I'll kind of clean up my free body diagram a little bit and redo it here and say this is going to be my pivot point right here. That little point where it's trying to come over the obstacle. You might say it's the top of the curb. But what I am trying to say then is I've got the tension here making it 1 torque will go up. That would be in a clockwise direction, so that might be a negative torque. And the other, the weight of it, is pulling it down, it's pivoting it in a clockwise direction. I'm sorry, a counterclockwise direction, so that's a positive torque. So, using the idea of equilibrium, the sum of the torques is 0. We're just right at that edge. Let's calculate these torques. Okay. So, we can think about which formula here to use. Maybe the thing to do is to do the torque from the tension first and then look at the perpendicular distance. Because if the whole distance is r and this little curb or obstacle is d, this would be r minus d. Nice. So using this formula for the torque, I would say the distance is r minus d, and the amount of force is T. And again, this one is kind of, you got to kind of imagine holding it right here. So I'll use my pen and then pushing it this way. That'll make it go clockwise. So that's a negative torque. Now, the other one, and imagine holding the pin here and pushing this direction, so I'll push down. That makes it go counterclockwise direction. So there's the torque. And the distance would be here. Here. And this one might take a little bit of thinking. In fact, maybe if I put a different color on here, remember this is an R. And we just talked about this vertical height, but I'll put it over here as R minus D. And this is R. And I kind of would like to know that perpendicular distance right there. Why don't I just call it X? But I'm hoping you can see a Pythagorean theorem here that says X squared, okay, plus R minus D squared is equal to R squared. And so I'd like to find this X. Okay, so X squared. And then this would be an R squared minus 2dr plus d squared equals R squared. And luckily, there's an R squared on each side. So it looks like X squared would be, and I'll move this over, 2dr, so positive, and then minus d squared. Maybe I will even factor out a d. Or maybe not. Let me just do x. So square root of 2dr minus d squared. Okay. So there's the x. All right. Okay, so coming over here, I've got the distance x, square root of 2dr minus d squared. And the force is capital mg. And so imagine moving it to this side, so I'll get tension, and that changes the sign, and then dividing. So I've got an r minus d in the bottom, and in the top I got a square root of 2dr minus d squared mg. And I'm just kind of looking here. Does it look like anything would simplify? I'm not seeing it. I could do this, but I don't see much of an advantage here. If I factored out a d, I'd get a 2r minus a d. And then I'd get an R minus D. Yeah, I don't see anything better. So I think that's the best we can do. Now, I suppose there is one more step, because technically the question, I think it said, how much mass needs to be put on the pan. So what I've technically solved for is the tension. But remember we said earlier on that the tension would be the weight on the pan. And the weight on the pan would be the mass added times G. And so this little m, what you put on the pan, we would divide a G away. And so it would just be the square root of D to R minus D over R minus D times capital M. So some number, some prefactor times the mass of the will. And of course, not a surprise that this prefactor is based upon how big the obstacle is in comparison to R. Okay, hope that helped.